Okay, so this is my video for the Chapter 13 homework assignment. And this is starting with Part A, which had to do with energy. And so in this first problem here, we have this ore mixing operation here, it says. And this bucket full of ore is traveling to the right with an initial speed of 10 feet per second. And the problem wants us to find the maximum horizontal distance once this comes to an abrupt stop. So right when this stops, this bucket of ore is going to swing, and it wants to know how far to the right it goes. And so to solve this problem, first thing I did was write down the equation that we've been writing in this chapter, which is right here, which is the kinetic energy plus the work equals the kinetic energy after kinetic energy 2. And so I kind of drew a free body diagram, and then I drew what we know on the picture here to kind of help me visualize that. And what we're looking for is this x distance from here to here from what I drew. And so thinking about this problem, we know that when this is at its max distance or max height, the velocity at that point will have to be 0. And so we can set the right-hand side of this equation equal to 0 here. And then on the left side, we were given this initial velocity here. And so we need to find this delta y here is the change in height between when it was 30 feet versus this h here. So this is the delta y here. And we don't know that, but everything else here we know because the masses will cancel out and we were given the velocity. And so all I did was cancel the masses, rearrange this equation, plug in the 10 feet per second, and solving for delta y, we get that that is this 1.5528 feet, and that's from here to here. And then at this point, all we need to do in the problem is a little geometry. So we have these two triangles here, so I redrew those here. We know that this length L is 30 feet, and we can calculate this using the delta y that we found, so we know that's 28.447 feet. And so I used those two to find this angle here. I called it theta. And then once I had that angle, then I could use that angle to find this distance here, x. We could have also used Pythagorean theorem, but I decided to use sine and cosine of the angle I found anyway. So that gives us the distance here that the bucket traveled after it came to an abrupt stop. And that answer was right here, 9.527 feet. So that's the answer for this one. On problem number 2, we have this truck here that's traveling up this hill. And the first thing the question wants us to find is the force at the wheels of the cab. And so it tells us the weight of the truck and the trailer. And so for part A here, I added those together to get our total mass of 7,200 kilograms. It gives us the speed at point A and point B. And so I converted those to meters per second so we could use them in the standard unit with everything else. And then I drew this free body diagram here. And I had to look this up, but it tells us that the incline of the road here is a 2% grade. And what that means is the height is 2% of this distance. So if we take 300 here and times it by 0.02 or 2%, that tells us that for the 300 meters that we traveled up the incline, we had a vertical rise of 6 meters. And so that's important for us to know. And then what I did was write our special equation here with kinetic energy and work. And so we know kinetic energy is 1/2 mv squared. And then for the work is force times distance. And so in the x direction, we had the force of the tires, which is what we're looking for, force at the wheels. and then minus because it's in the opposite direction of the motion, minus the weight times the 6 that we just calculated because of the 2% grade, and that has to equal 1/2 mv final squared, which was given. And so from this equation we have everything we need to solve it, except our one unknown, the force at the wheels that we're looking for. And so it's just a matter of plugging in everything here and then solving that to get this force here. And then on part B, the question asks for the average force in the coupling between the cab and the trailer. So this time we didn't want the total mass, so I split it up and just looked at the mass of the trailer. And then we use our same equation here for kinetic plus work equals the kinetic on the other side, the final at B. And so similar to part A, we split that up into 1/2 mv squared. And this time we can plug everything in and find the force on the tires. And so plugging that in, similar to part A, we find that the force at the tire between the force on the trailer between the two is this 5.5595 times 10 to the third newtons. And that is the tension between the trailer and the truck as it goes up this hill. On problem 3 here, they gave us a diagram of this train, the subway train, and they tell us that the train is moving to the left at 30 miles per hour, but only the brakes in cart A are applied, and then the train comes to a stop, and the first thing they want us to find is the distance from when the brakes are first applied to when the train completely comes to a stop. And so looking at the problem, there's a couple things that we can convert into units that would be easier for us to use. And so we know that 1 ton is 2,000 pounds. And so for the first part of this problem, we're going to want to treat this train as one body. And so I added these three together, the 40, and the 50. And then I multiplied by 2,000 to give us a total mass in pounds. And then I took our initial velocity here, which we called V1, and I converted that into feet per second, which is 44 feet per second. And then I drew this free body diagram here, so we know that we have the weight of the subway train going down, the normal force opposing that going up, and then the force of friction going opposite the direction of the train to try and slow it down. And so in order to find the distance, we use this formula here with work. And so we have the kinetic energy at point 1 plus the work between 1 and 2 equals the kinetic energy at point 2. But we know that in this situation, the final velocity of the train will be 0, so this term will all just go to 0. And then all we have to do is plug in what we know here. And so for this first term of kinetic energy, we have the weight of the entire train divided by gravity to give us the mass, and then we multiply by our initial velocity, and then we're subtracting off the force of friction here, which we know is the normal force, times the coefficient of friction, which was given to us in the problem, that was 0.35. And because the brakes are only applied to train A, that weight is only the 40 tons or 80,000 pounds. And then this is also multiplied by D because we know that work equals force times a distance. And so after plugging in everything we know into this equation here, we can solve for D and find out the distance that this train travels is 279.15 feet. And then for part B, the question asks us for the distance required to bring the train, the force in each of the couplings. So the force between A and B and C here. And so for the force between A and B, I decided to isolate train A because I didn't want to worry about both couplings at the same time. And so I drew another free body diagram here. And so in this situation, we have the coupling here between the trains as a force. We have the force at A from the brakes, and then we have our normal force in our weight. And so similar, we use this equation again. And once again, we're coming to a stop, so this right side of the equation will go to 0. And so in this instance, though, we're not calculating the total mass of the subway train. We only want to consider this cart on its own, cart A. And so that one is the 40 tons or 80,000 pounds. And then for work, what we have is our distance, which we calculated in part A, and that's multiplied by our forces. And on cart A, there's two forces now. There's the force from the tires as they brake, and then there's also this coupling force, which is what we're trying to solve for. And so we know the braking force here from up above. So that leaves us with only one unknown, the coupling force AB right here. And so solving that, we get that is equal to negative 19,380 pounds. And the negative sign tells us that that is in compression. That joint is in compression. And then it wanted us to do the same thing for cart C. And it's a similar process. Everything is set up the same, except cart C does not have the braking force on it. It is just sliding along without its brakes on. And so we don't have that term. But we solve that and we get that the coupling force between B and C is negative 8,617. And once again, it's negative, telling us that it is in compression. And so that's all for question 3. This is problem number 4. And in this problem, we have this diagram here given to us. This guy that's dropping this ball, and it's attached here with this rope with length L that's given to us. And the question wants us to find out what this angle will be when this rope breaks. And we know that the maximum tension that this rope can handle is 2 mg. And so to solve this problem, the first thing I did was write our equation here that uses potential energy and kinetic energy together. And then looking at this problem, we know that the initial kinetic energy when he drops this ball, it's traveling with 5 meters per second, and so this is not 0 to begin with. It's actually 5 meters per second, so we put that in for velocity here. And then the potential at this height here, I chose my reference to be down here at the bottom of the swing is 0. And so that is a length of L up from there. So the potential there is mgl. And then once this ball starts moving, we will have a kinetic energy of 1/2 mv2 squared. And our potential, I designated it as h. So whatever angle this is at here, h will be this distance here that's left. And that is a portion of the length L before it gets down to the bottom. And so what I did next was I drew this triangle here and tried to figure out a relationship that involved theta. And so as this ball is swinging down, we need to know this y here, which is the difference between h and L. So L minus h will equal y. And so as we subtract this over to the other side of the equation, we know that this y distance here will be L minus h, and that will be our potential difference. And so drawing this triangle and using trigonometry, we can find out that y will be 2 sine theta, and theta is the angle we're looking for. And so we can plug that in here for L minus h, because that is what this y will be. And then all I did was solve this equation for velocity squared. And so we have this equation here, but it has 2 unknowns. We don't know theta, which is what we're trying to find, but we also don't know the velocity at that time. And so going back to what we learned in chapter 12, we can use kinetics to derive another equation. And so I did that over here. So this is my free body diagram for the first part using potential and kinetic energy. And then this diagram here was the one I created for the kinetics part. And so this is the force diagram here. And then that has to equal our kinetic diagram, mass times acceleration. And so for the force diagram, we have tension in towards the center of the circle, and then gravity, our weight pulling us down. And that has to equal mass times acceleration, and we know that this is a normal acceleration pointing in towards the center of the circle, and that there will be no acceleration in the other direction. And so what we do at this point is just take this diagram and create an equation from it. So here are our forces that equal mass times acceleration. So we have tension minus the angle of mg in that same direction. And then we can replace our acceleration with v squared over rho. And in this case, our radius rho is just the length of our chord L. And so rearranging this equation and solving it for v squared is what I've done here. And then our tension, we're looking for the tension when it breaks, and the problem tells us that T max equals 2 mg. And so substituting in 2 mg for tension here gives us this equation here. The masses cancel, and the mass is also canceled in this equation, so this is independent of the mass, so we didn't need to know that. And then all we have here is two equations with two unknowns, and so I just took this v squared equation here and this v squared equation here and set them equal to each other, and that's what this equation is here. And then just plugging in gravity into this and simplifying it, we can have what sine theta is equal to right here, and then using the inverse of sine, we know that theta is 14 degrees when the rope breaks. On problem number 5 here, we have this chairlift that's transporting skiers up this hill, and the question wants us to find the average power required to do that. So how much power a motor would have to pull the skiers up the hill. And so when I first started solving this problem, I was using the part where the problem tells us that there is a speed of 75 meters per minute taking them up the hill this way. But looking at the question closer, we realize that we don't actually need to use that information. So this hill could be jaggedy or whatever, and it doesn't really matter what path they take up here, because the problem tells us that we are moving 1,000 skiers every hour. And so I missed this per hour the first time reading through the question, and that is very important to see. And so in order to solve this problem, the first thing I did was get a total mass of the weight of all the skiers that go up the hill. And so that's 1,000 skiers times the weight of each skier, the 70 kilograms. So the total mass is 70,000 kilograms. And then we know that power is force times velocity. That's the definition of power. That's our formula that we use. And so looking at this problem, I broke this down and tried to find force and velocity. And so our velocity, we know, is our delta y over delta t, or basically our change in height over change in time. And so we know that the skiers are going up 300 meters, and they do that in 1 hour, or 3,600 seconds. And so taking 300 divided by the time, 3,600 seconds, gives us our velocity of, right here, 0.0833 meters per second. And then as far as the force acting on this system here, the only force acting against this motor pulling them up the hill is the force of gravity, which is mg. And we know m, which was what we calculated here, and g for gravity is just our 9.81. And so just putting all that together and multiplying it out gives us a power of, right here, 57,202 watts to carry the skiers up this hill. So that's the answer for part A. And then part B is asking us to find the required capacity of the motor if the mechanical efficiency is 85%, and if 300% overload is to be allowed. And so the first thing we have to do is figure out that 300% overload. And so this is 100% right here, the power that we calculated, but we're going 300% overload on top of that. And so it would be 3 times this is our 300% overload plus the original, or basically 4 times our original power that we calculated here will give us our 300% overload. And so this is what we get for our new power, calculating that. And then our formula for efficiency is eta equals power out over power in, and eta we know is 0.85 because that's the efficiency given in the problem. And so rearranging that, we know we can divide by 0.85 to find the initial power in that we need, and that comes to this 262,000 watts. So that's the answer for this one. Okay, so this is problem 6. In this problem we have this collar here at A that's attached to a spring at the origin here. And this collar is going to slide down to B and then back to C. And the question wants us to find 2 things. It wants us to find the velocity when the collar reaches B and the velocity as it reaches A here. And so looking at what the problem told us, it gave us the mass of the collar is 2 kilograms. It gave us our spring constant K, and it also told us that the spring is unstretched here at C. So the spring is unstretched at 150 millimeters. And so writing our equation that potential 1 plus kinetic 1 equals potential 2 plus kinetic 2 right here, we can find out what the problem wants us to solve for. And so I kind of did this in steps here. And so we calculated the difference here between this spring and what the spring would be here and here to find out how much the spring stretched. And so when the spring was at B, it stretched 0.05 meters. And when the spring was at A, it was stretched more, it was stretched 1 meter. And then at C, we know that it was undeformed or not stretched. So that's its normal state. And so the potential at A, I did here, which from the spring, using that we just calculated. So it's just 1/2 our given K times how much the spring has stretched, which comes out to 3 joules. And then the same thing for B, except we have a different amount that the spring stretched, which is right here. And so that comes out to 0.075 joules. And then at C, there will be nothing from the spring because the amount of stretch is 0 there. And then as far as the potential energy, that comes from gravity. I did that right here, so that would be negative mgy. And so stating that the bottom here is 0, that's my reference. And then the difference here, so this is 0.2 at B, and so calculating that, the difference between B and the origin is 0.2 meters. And then we know our mass was given to us, and we know gravity, and so we can calculate the potential from gravity there. It comes to this negative 3.924 joules. And then we have everything we need to plug into our formula. So here I rewrote the formula. So the before was the potential and kinetic at A, which is right here, and then after is this is the kinetic and the potential at B. And so plugging in what we found for those gives us this equation here. And then all we had to do was solve that for what we're trying to find here, our velocity. And so that comes out to 2.48 meters per second at B to the left. And then we just had to do the same thing at C, so I replaced B with C. And In this instant, the spring constants were 0, so we didn't have to worry about those. On this one, we did have to bring those down, but this one didn't have that, and so solving that, we can find that the velocity at c is 1.732 meters per second, and that one is up because it's following this track. Okay, so this is problem number 7. In this problem, we have a spring at the bottom of an incline, and this package here is going to come down and hit the spring. And the problem tells us that the spring is actually already compressed a little bit before the package hits it, so we need to take that into consideration when we solve this problem. So I drew a little 3-body diagram here to kind of think it through, and then I also wrote this equation here for the kinetic energy plus the potential energy initially has to equal the kinetic energy plus the potential energy finally after it's come to rest here. And so since we know that the package will actually come to rest here, is what we're looking for, the final kinetic energy of the package will be 0. And so I cross out and put a 0 through it. The problem gave us quite a bit of information. It told us the initial velocity, so the kinetic energy here will not be 0. And then it also gave us the mass and the spring constant. And so taking this equation and breaking it down, before at position 1, this is the kinetic energy, and then there are 2 potential energies acting on the package at 1. So there's the energy from gravity, mgh, pulling it down, and then there's also the spring here because it's already compressed, so that's the 1/2 kx squared. And in position 2 we have those same potential energies, but the kinetic energy is 0. And so looking at this problem, there's a couple things we had to figure out. So I drew this triangle here to help me figure out the difference in height here that the package goes down. I labeled that h, and so using the sine of our angle 20 degrees, we can figure out what our height here is. And then we know the mass was given, and we know the gravity constant of 9.81, so that gives us everything for this term. Everything for this term was given in our problem. This term has the x in it, but that's what we're trying to solve for. But the amount that the spring was compressed was actually the 0.5, which was given to us. And so substituting everything we know from the equation into this, we get this really long equation here. The tricky part of this problem was the potential energy on the height after the package comes to a rest, because we don't know what the height will be. It will have compressed the spring a specific amount, and we don't know what that is, but that's what we're trying to find. And so just like before with h, I drew the same triangle with x, and that gives us the same relationship for what x is equal to, and so we can solve for that. And so plugging everything in, we get this equation here. And then I just plugged in a lot of these numbers into my calculator and tried to simplify it, which gave us this here. So we had a constant on this side and 3 x terms. And so this turns out to be a quadratic equation that we can plug this into, which gives us 2 values for x. But one of those values is negative, and that doesn't really make sense for this problem. And so we choose the positive value, and so we know that x is the 0.26882 meters. And so that is the answer. Okay, so this is problem number 8, which is the first problem of part B. So the rest of these problems start to deal with momentum and impulse problems. So it's the second part of chapter 13. And in this problem here, we're given this truck that's driving up this incline ramp. And the first thing the problem wants us to find is the magnitude of the braking force. And so to do that, the first thing I did was draw this little free body diagram and label my axis there with positive x going up the ramp to help me kind of think through the problem. Then I also looked at what the problem told me, so these were the things I was given in the problem. And the problem also told us that the truck weighed 10 tons, and so we know that 1 ton is 2,000 pounds, so 10 tons would be 20,000 pounds. And then converting that into mass for our equation, we divide by gravity, which is 32.2, to get a mass of the truck of 621. And so to solve this problem, I used this equation here that we've been using in this class. And so we have our momentum before and after, and then plus our impulse. And so we have pretty much everything we need at this point. We just need to recognize that since we don't need to integrate in this instant because force isn't a function of time, that we can just know that impulse will be force times our delta t, which was given to us. And looking at our free body diagram, we know that our force is F, which is what we're trying to find, the braking force, plus mg sine 15, the angle of the ramp here. And so plugging in what we know is right here. That's what I've done, plugging in the initial and final velocity as well as the mass that we calculated. We can solve for F, and then I labeled what F is here, and then solving for our braking force, we know that that is equal to 2,280 pounds. And so that was the answer for part A. And then in part B, we wanted to find the magnitude of the braking force in A, which is here, and then for part B, we wanted the additional time required for the truck to stop. And so what that means is when the truck is stopped, the velocity will be 0, so we can use the same equation and set the right hand side of the equation equal to 0. The braking force here is what we calculated in part 1, so we have that, and now we have everything here except for the time. And so plugging in everything that we know is right here, and then solving for time, we get the time equals 9 seconds. But the problem wasn't asking for the total time. It was actually asking for the additional time. And in part A, we know that the truck already traveled for 6 seconds, and so the delta t there would be the 9 that we calculated minus the initial 6 for an answer of 3 seconds. Problem number 9 here is another problem where we have a pulley that we need to take in consideration. And so the first thing the problem wanted us to find was A, it wants us to find the time at which the velocity of collar B will be 2.5 meters per second to the left. And so on this collar here at B, there's actually 150 Newton force pulling to the left, as well as the force caused by weight number A falling towards the ground. And so we had to take both of those into consideration. So I started by drawing a moment diagram of block B here. And so we have the momentum initially plus the impulse equals the momentum after. And then I drew arrows designating the direction for each of those. And reading the problem, we know that it starts at rest, and so this first momentum will be 0. And so creating an equation from this diagram, we can create this equation here, which leaves us with an unknown here of tension that we need, and time as well, because we know that impulse is force times time, and so that's why these forces are multiplied by a t here. And so in order to solve this, we're going to need another equation, and we can get that equation from block A here. And so what I did was I looked at this pulley system, and right here I created a relationship between this collar and this block, a relationship from their tensions and their velocity. And so we know those relationships, we can compare the two equations. And so then I drew another moment diagram here for the block A. We know it also starts at rest, so the first term here is 0. And then impulse also has two terms, the tension of A pulling up and the weight pulling down. But I replaced this tension with A with what we know that it is here, so we know that it's half of tension B, so I put that into our equation here. And our weight is just mg pulling it down. And then on the right side of the equation we know both of these. And so that leaves us with two unknowns and two equations. We have this equation here and this equation here. And our two unknowns are the two things that the question asked us to find. And so just solving that system of equations, we know that the tension in the cable is 56.8 newtons and the time is 0.55 seconds. And so that's the answer. Okay, so this is problem number 10. This problem has a ballistic pendulum, and I remember doing some of these from Physics 1. They're kind of an interesting concept. So basically the block B here is at rest, and then once the bullet is fired, it hits this block and they stick together, and then the pendulum will swing up to a height. And by knowing that height, we can figure out the initial speed of the bullet, which is what they want us to solve for first in this problem. And so what I did here was I drew a moment diagram. So before we have the block at rest and the bullet traveling to the right. And then that equals the momentum after, because we know momentum is conserved in a closed system. These are internal forces here, so they're conserved. And so that has to equal both of the momentum after. And since the bullet and the block stick together, we know that the value for E has to be 1. And so turning this into an equation here, we know that this is the momentum of the block or the bullet before, and this is the momentum of the block before, and then these two terms are after. And so what I did first was I plugged in what we know here. So we know the velocity of the block was 0, and so that term is 0 to begin with. The velocity of the bullet is what we're trying to find, but we're given the mass. And then on this side I factored out the velocity after, because we know that the velocity of the block and the bullet will be the same because they're stuck together. And so we still needed to find the final velocity here because we have two unknowns. And so in order to solve that, I went back to our kinematics here, and we know that the potential energy here has to equal the kinetic energy, and so that's this equation here, and the masses cancel, and then this is what we're left with here. And so plugging in what we know, we can use Pythagorean theorem to find out the height here, so in this part of the equation, and that's what this is here. So I just use the cosine of the angle to find that height, which comes to 1.1 meters. And then from there we just have to plug everything in and solve for the final velocity of the block and the bullet, which is 4.6456 meters per second. And then plugging that in over here, that leaves us with just the one unknown, the velocity of the bullet. And so then we can solve for that. And so that's the answer for part A right here, the 778 meters per second. Part B asks us for the impulse imparted by the bullet on the block. And so in this instance, we don't want to treat them as an entire system because we're looking for the impulse. And so what I did here was wrote an equation for initial momentum plus impulse equals final momentum. And we know, looking at our diagram, that the impulse will have to be negative because of the direction here, and that the initial velocity of this block will be 0. And then the final term here is the mass of both the block and the bullet, which is right here. So the bullet we had to convert into kilograms. And then right here, this is the velocity after, which we calculated right here when we did part A. And so plugging all of that in, we get the impulse is 4.67 joules. And so that's part B. The final thing this question wanted us to find was the force on the cord immediately after impact. So how much force is on this cord here? And so I drew a diagram of that right here. So we have tension going up and mg going down, and those are the only forces there. And then we know the acceleration will have to point up towards the center of the circle, because once the bullet hits here, this rope will swing in a circular pattern, and we know that the acceleration is always towards the center. And so taking this and creating an equation from it, we get this equation here, and then we replace our normal acceleration with v squared over L, and L is our 2.2 meters here, the radius of that circle. And then all we have to do is plug in everything we know. So we know the velocity, once again from up above, the length was given to us. And so solving that, we find that the tension is 19.74 newtons. Okay, so problem 11 here was kind of an interesting problem. It's similar to one of those toys that you can see on people's desks sometimes where they pull the ball back and it hits these balls here. But the difference in this case is there's a little space between each of these balls, and so that changes the effect a little bit. And so the first part of the question, it wanted us to find the velocity of A and B after the first collision. So after this A prime hits right here, what is the velocity of A and B? And so I labeled my direction positive to the right here. And in the beginning here, we only have motion in A here, A prime, and then after both A and B will be moving. And so in order to solve this, we used two different equations. We used the equation that has the E value in it, and then we also used the equation of conservation of momentum. So momentum before has to equal momentum after. And in this case, we know that the mass is constant for each of these blocks. It has equal mass. That's very important. And that allows us to cross out the mass in each term here because they're the same. And then in the top equation here, we know that this block is not moving when this is first dropped. And so we can eliminate that because it will be zero, because it has zero velocity. So looking at that, that leaves us with this equation here. And then in this equation here, we can also cross out VB here because of the same reason. This ball B is not moving initially. So once we have these two equations here, then all we have to do is basically solve the system of equations here for VA prime and VB prime. And so this is the answer I got for both of those. They're very similar. This one just has a minus sign and this one has a plus sign. And then part B was very similar here. We used the same two equations and similar things cancel out. However, the difference in part B is that we basically have VB prime here becomes VB down here. And so that's why I put the double prime here, because that's, so there's this first collision between A and B, and then the second collision between B and C, that would be V double prime. And so basically all we had to do was substitute in VA prime and VB prime here into what was VB before, and then once again solving the system of equations, which gave us this solution here. And the difference here was obviously the parentheses were squared and we had a 4 on the denominator. Okay, so this is problem number 12 here. In this problem here we have this block B that's moving to the left with an initial velocity v0, which is given to us. That's 2 meters per second. And it's going to hit this ball A that's connected to this string, and after that collision, ball A is going to go up to a certain height, and then block B is going to travel a distance x until it stops. And the problem wants us to find both of those. It wants us to find this value for h and the distance x. And so looking at this, we know that we have a system here, and in this system that momentum will be conserved. And so I drew this momentum diagram here. So this is the ball in the block before. So the ball is 0. It equals 0 because it has 0 velocity. And the momentum of the block before is mvb1. And then after, we know that both will be moving to the left. And so looking at that diagram, we can create an equation from that. So this is the mass times the velocity of the block before. And then afterwards here we have the mass of the ball times velocity of the ball plus the mass of the block times the velocity of the block. And so that gives us this equation here. And then the question also tells us the value for E, which is 0.8. So we can use our other equation, which is right here, that deals with E, the eccentricity value, and plug in what we know. And so the initial before, the ball was 0 and the block was 2. And so we can rearrange this equation here, and then we have two equations here with two unknowns. And so solving this system of equations, we can find the velocity of the ball and the velocity of the block after impact. And so using that information, we can answer what the question wanted us to find. And so for part A, to find this height of the ball, we want the final velocity, or the initial velocity of the ball here, right after impact. And we can use our equation where we know that potential energy has to equal kinetic energy. And so the kinetic energy caused by block B hitting ball A is right here. The mass of the ball is the same, so those cancel. And the velocity is what I just showed up here. And so plugging all of that in, we know the constant for gravity, and we found the velocity, and so we can solve for the height h, and that comes to 0.2935 meters. And then in part B, we had to use our conservation of energy equations. So this problem used basically all of the tools from chapters 11, 12, and 13 to solve it, which is kind of interesting. But this is the equation we had to use for part B right here. And then I drew a diagram of this so we could kind of visualize it. And then writing this equation from what we see, we know that the kinetic energy before plus it's a negative mu mgx because it's moving to the left, and so after that we can solve this, and I just kind of canceled out the mass because it's the same, and then rearranged our equation and plugged in what we knew, which gives us this equation here, which only leaves us the x, and we can find x because this equation is the one that deals with energy, which we know we have distance in that because of the work term. And so then all we have to do is solve this equation here, and we get that x is equal to 0.05437 meters. And so those are the answers for part A and B on number 12.